Beams are structural members, which are most commonly used in buildings. In a beam, transverse load is acted, which in fact comes from the slabs to the column or walls. For analysis, beam can be separated out from beam-column system. Length of the beam is much higher than its lateral dimensions. Axial strain developed in a beam is very small compared to shear strain, or strain induced due to bending. So for design purpose of beams, analysis of shear force and bending moment induced are of utmost importance. The interesting thing is that, you can draw shear force and bending moment distribution along any beam, by understanding what exactly is shear force, and bending moment. First, shear force. Shear force is the resistance created in beam cross-sections, in order to balance transverse external load acting on beam. Consider this beam, it does not matter from where you take a section, when you add forces acting on it, it should be in equilibrium. Shear force is induced exactly for this purpose, to bring the section to equilibrium in vertical direction. It acts parallel to cross-section. Usual sign convention is as follows. So just by applying force balance in vertical direction, on the free body diagram we can determine value of shear force at a particular cross-section. Now we can apply same concept in different cross-section and find how shear force varies along length of the beam. But balance of transverse forces alone does not guarantee equilibrium of a section. There is another possibility of beam rotation, if moment acting on it is not balanced. If this is the case, a bending moment will be induced in cross-section of beam, to arrest this rotation. It will be induced as normal forces acting on fiber cross-section, as shown. Resultant of those forces will be zero, but it will produce a moment, to counterbalance the external moment. Sign convention of bending moment is as follows. So we can calculate moment induced at any cross-section by balancing the external moment acting on the free body diagram. With these concepts developed, we can easily calculate distribution of shear force, and bending moment, along the length of the beam. We will see some examples. For this cantilever carrying 3 loads, we can start analysis from the free end. So for between A and B, if you take a section, the only external force acting on it is F1. So a shear force should induce in section to balance this force. So value of shear force between A and B is F1. But force balance alone does not guarantee equilibrium of the section. There is an external moment on the section. So a bending moment will be induced in section, in order to balance the external moment. Since value of external moment is F into X, bending moment will vary linearly. Between B and C, effect of force F2 also comes. So shear force becomes F1 plus F2. And in bending moment, effect of F2 also gets added. Similar analysis is done between section C and D also. So SFD and BMD of this problem would look like this. Now consider this problem. A simply supported beam with uniformly distributed load. First step here would be determination of reaction forces. Since the problem is symmetrical, reaction forces will be equal, and will be half of total load acting on beam. Let's start analysis from point A. If you take section between point A and B, it should be in equilibrium. So shear force will have equal magnitude of reaction force. So bending moment also gives a linear variation. But after point B, effect of point load and distributed load comes. Effect of distributed load is something interesting. Take a section in BC. In this section, along with 2-point loads, there is a distributed load also. This distributed load can be assumed as a point load passing through centroid of distributed load. Value of that is u into x minus L by 3. And it is at a distance x minus L by 3 by 2 from section line. So shear force will have one more term, which comes from distributed load. From the equation it's clear that shear force varies linearly. You can easily predict how bending moment varies along length from the same force diagrams. Since this equation is quadratic, it will have a parabolic shape. Same procedure is repeated in remaining section. Since this problem is symmetrical, bending moment and shear force are having a symmetrical distribution. Hope you got a good introduction on analysis of beams. Thank you.